Hello students, welcome to lecture 10, Cramer lower bound 2. Let us recall this Cramer theorem gives a bound on the variance of an unbiased estimator in terms of Fisher information statistics. Now what is Fisher information statistics? I theta, that is expected value of del theta square, is the Fisher information statistic, which can also be expressed as I theta is equal to minus of expected value of del 2L del theta square. Shear theorem, Cramer theorem for an unbiased estimator theta hat under certain regularity conditions, variance of theta hat is greater than equal to 1 by I theta. So, this is the statement of Cramer theorem. Therefore, Cramer lower bound CRLB for variance of theta hat is equal to 1 by I theta, that is equal to 1 by expected value of del L del theta whole square, and this can be also written as 1 by minus expected value of del 2L del theta square. And one important point is CRLB is reached if that first order partial derivative of log likelihood function, that is del L del theta, can be expressed as C into theta hat minus theta, where C can be a function of theta. In this lecture, we will discuss our Cramer lower bound for estimators of function of a parameter g theta. Earlier we discussed the estimator for theta, but now we will discuss what will be the CRLB for an unbiased estimator for g theta. Second thing we will discuss is CRLB for estimators of vector parameters. Suppose multiple parameters are there, theta 1 up to theta k, which are arranged in a vector. So, what will be the CRLB for the unbiased estimators for this vector parameter? Let us revisit the condition for achieving CRLB. We know that for achieving CRLB, we have the equality condition given by del L del theta is equal to C times theta hat minus theta. Squaring and taking expectation, we get that E of del theta whole square is equal to C square times E of theta hat minus theta whole square. So, we will square this and take the expectation of both sides. So, that way we get this. From this we get C square is equal to E of del theta whole square, that is I theta divided by E of theta hat minus theta square, that is equal to variance of theta hat. So, this is the expression for C square which we derived in the last lecture. Now, at equality, we know that variance of theta hat is equal to 1 by I theta. So, if I put variance of theta hat is equal to 1 by I theta, then I will get C square is equal to I square theta. So, from this C square is equal to I theta by variance of theta hat, and variance of theta hat is equal to 1 by I theta at equality, that is the condition. Therefore, we will get C square is equal to I square theta, implied that C is equal to I theta. Therefore, CRLB is reached if del L del theta is equal to I theta into theta hat minus theta. We will discuss about CRLB for the estimators of a function of a parameter. So, suppose g theta is a function of the parameter theta and g hat theta is an unbiased estimator of g theta. Then under the same regularity conditions, variance of g hat theta is greater than equal to g dash theta whole square divided by I theta, where g dash theta is the first order derivative with respect to theta. So, this is the Cramer theorem for the function of a parameter, and the equality in shear bound for this inequality, the equality will be reached if first order derivative of that is L x theta, that is first order derivative of the likelihood function, is equal to I theta multiplied by g hat theta minus g theta. So, you can factorize del L del theta into form I theta into g hat theta minus g theta. So, this is the condition for reaching the shear bound. The proof of the above is similar to the proof of shear theorem we have discussed earlier. We will consider one example. Let x1, x2 up to xn be IID Poisson random variables with unknown parameter lambda. Suppose g lambda is equal to lambda square. So, find the shear bound for the unbiased estimator of g lambda and hence examine if it is achieved. Now, xi's are IID. We will find out the likelihood function of x1, that is equal to PMF Px1 as a function of lambda, that is equal to e to the power minus lambda into lambda to the power x1 divided by factorial x1. We will take the logarithm, therefore, it will be minus lambda plus x1 into log of lambda minus log of x1 factorial. And if we take the second order partial derivative with respect to lambda, we will get del 2L del lambda square is equal to minus x1 by lambda square. So, for information we have to take the expected values, therefore, I1 of lambda will be E of x1 divided by lambda square, that is equal to 1 by lambda. Since there are n IID random variable, therefore, I lambda will be equal to n times I1 lambda, that is equal to n by lambda. Therefore, shear LB is equal to g dash lambda square divided by I lambda, that is equal to 4 lambda square, because if we take the derivative, this will be 2 lambda, square will be 4 lambda square divided by n lambda, and that is equal to 2 lambda cube by n. This is the shear LB for any unbiased estimator of g lambda. Now, let us examine the equality condition. The likelihood function we are again rewriting, this will be p of x vector lambda as a function of lambda is equal to product of e to the power minus lambda, lambda to the power xi divided by factorial xi, I going from 1 to n. This is the joint PMF or likelihood function in terms of lambda. And taking logarithm, L x lambda will be equal to minus lambda plus log of summation xi I going from 1 to n plus terms not involving lambda. Therefore, del L del lambda will be equal to minus 1, derivative of this is minus 1 plus summation xi I going from 1 to n, and derivative of log m is 1 by lambda. So, that way this is del L del lambda is equal to minus 1 plus summation xi I going from 1 to n divided by lambda, and this can be simplified as n by lambda into summation xi I going from 1 to n by n minus lambda, and this we can write as I lambda into lambda hat minus lambda. Here it is lambda, not lambda square. Therefore, we conclude that shear LB is not reached by an unbiased estimator of lambda square. It is reached by an unbiased estimator of lambda, which is given by lambda hat is equal to 1 by n times summation xi I going from 1 to n. Now, we will be considering shear LB for estimators of vector parameters. Suppose theta 1, theta 2 up to theta k are k parameters which are represented as the vector. This is a k dimensional vector, theta given by theta 1, theta 2 up to theta k transpose. This is a column vector. This vector characterizes the likelihood function, and likelihood function is given by f x theta, that is f of x1, x2 up to xn, and parameters are theta 1, theta 2 up to theta k. Then the log likelihood function is given by we will take the logarithm. So, this is the log likelihood function. Now, because it is a function of several variables, we can get the first order partial derivative vector. So, we can take the del L del theta 1, del L del theta 2 like that. So, one column we can take, this column is the vector representation for the first order derivative del L del theta. Fisher information matrix. The Fisher information matrix is given by the I theta matrix, that is given by E of del L del theta. This is a vector into del L del theta transpose. So, this product will be a matrix, and then we take the expectation of the individual element of the matrix. So, E is performed on each element of the matrix. So, this is the Fisher information matrix, and it can be also shown that I theta is equal to minus expectation of del del theta of the del L del theta vector. So, that way this will become a matrix now, and that matrix is given by minus expectation of del 2 L del theta 1 square, del 2 L del theta 1 del theta 2, del 2 L del theta 1 del theta k, like that. Last row will be del 2 L del theta k del theta 1, del 2 L del theta k del theta 2, like that up to del 2 L del theta k square. So, this is the Fisher information matrix. Now, we will be considering unbiased estimators for vector parameters. That is our concern. Suppose theta hat is equal to theta 1 hat, theta 2 hat, etc. up to theta k hat transpose. This is a vector. Be unbiased estimator of theta. Theta is equal to theta 1, theta 2 up to theta k. So, then E of theta hat vector will be equal to theta, that is the unbiased estimator, and the covariance matrix of theta hat is defined by C theta hat, that is equal to E of theta minus theta hat into theta minus theta hat transpose. This is the definition of covariance matrix. Now, we examine some interesting properties of this covariance matrix. This diagonal elements C j j of C theta hat represent the variance of theta hat j. So, the jth diagonal element will be the variance of theta hat j. Similarly, C theta hat is a positive semi-definite matrix. That is very important. This covariance matrix is a positive semi-definite matrix. How do I define positive semi-definite matrix? For any real k dimensional vector z not equal to 0, the quadratic form, this quantity z transpose C theta hat into z will be always greater than equal to 0. This is the definition of positive semi-definiteness, and if it is greater than 0, then it will be positive definite. Now, test for positive definiteness is eigenvalues of positive semi-definite matrix are non-negative. So, if we get all eigenvalues greater than equal to 0, then it will be a positive definite matrix. And all the leading principal minors of a positive semi-definite matrix are non-negative. This is a test for simple case. Suppose I have some matrix like this A11, A12, A13 suppose, A21, A22, A23, A31, A32, A33. So, this is the matrix. Now, we have to consider all leading principal minor, that means we have to consider from the left hand side, we have to consider minor. First minor will be A11, this should be greater than equal to 0. Second minor will be determinant of this, and this should be also greater than equal to 0, and third leading principal minor is the entire determinant, that should be also greater than equal to 0. So, this is the test for the positive semi-definiteness. Now, we can state the CR theorem for vector case. Assume that the likelihood function, this is the likelihood function, satisfy the regularity conditions stated earlier. Then the covariance matrix C theta hat of any unbiased estimator theta hat, that is the covariance matrix, satisfy this relationship. covariance matrix minus I inverse of theta. I theta is the Fisher information matrix, that will be greater than equal to 0. So, C of theta hat minus I inverse of theta will be always greater than equal to 0 matrix. Where I theta is the Fisher information matrix and the inequality. Now, this inequality is a matrix inequality. This inequality with respect to 0 matrix implies that this quantity C of theta hat minus I inverse theta is a positive semi-definite matrix. So, we have to test whether this matrix C theta hat minus I inverse theta is a positive semi-definite matrix. This is the condition for Cramer lower bound. So, this C of theta hat minus I inverse of theta is a positive semi-definite matrix. Now, again this equality will be coming in the form of a vector, del L del theta will be equal to I theta, this is a k by k matrix into theta hat minus theta vector. So, this is the condition to test whether this shear bound will be reached. We will make some remarks. Suppose we have found the shear bound in terms of C of theta hat. What will be the shear bound for individual element of C theta hat? So, that the individual variance will be given by variance of theta I hat will be greater than equal to the I that is ith diagonal elements of I inverse theta. This is the variance of theta I hat. The above bound is larger than the one obtained by CRLB for theta 1 hat when other parameters are known. For example, we can find out individually the bound on variance of theta I hat, assuming that other parameters are known. In that case, we will get a lower bound. So, this bound what we get through this matrix from this matrix, and that is larger than what we get individually, that is larger than the one obtained by CRLB for theta I hat when other parameters are known. We will illustrate this concept. Finding I inverse theta is difficult except when xi's are independent. In that case, I theta is a diagonal matrix. So, finding out I inverse theta is easier. We will consider an example of CRLB for multiple parameters. Suppose xn, that is equal to a plus bn, this is a constant and there is a trend here bn plus vn, where vn is a normal Gaussian noise and noise sequences are independent, a and b are the unknown parameters. Here parameter vector is equal to a b transpose. Now, we have to find out the CRLB for theta. So, in this case, because these VI's are independent, therefore, we can write this joint PDF, that is the likelihood function, that will be given by this expression 1 by root over 2 pi sigma square to the power n into e to the power minus half of 1 by 2 sigma square into summation xi minus a minus bi whole square I going from 1 to n. So, this is the n dimensional Gaussian, and we can take the logarithm to get the log likelihood function given by this. This is the expression for log likelihood function, and if I take the first derivative with respect to a, we will get this quantity. Similarly, del L del B will be given by this because bi is there. So, we will have I here, and similarly we can take the second order derivative now. Suppose del L del A is given. So, we can find out del 2L del A square, we can find out del 2L del A del B, del 2L del B square. So, these are the values. Therefore, I will be equal to 1 by sigma square times this matrix. First element will be n, then first row second element will be n into n plus 1 divided by 2. Similarly, second row first element is n into n plus 1 divided by 2, n plus 1 into 2n plus 1 divided by 6. This is the information matrix. Taking the inverse, it is a 2 by 2 matrix, we can easily take the inverse. The inverse I inverse is given by sigma square times first element is 2 into 2n plus 1 divided by n into n minus 1 minus second element is minus 6 by n into n minus 1. Similarly, this element and this element is same. This last element is 12 by n into n square minus 1. Now, this term is related to the variance of first parameter, that is variance of A hat. Similarly, this part is related to the variance of the second parameter, that is variance of B hat. Therefore, variance of A hat is greater than equal to 2 into 2n plus 1 times sigma square by n into n minus 1, and variance of B hat is greater than equal to 12 sigma square by n into n square minus 1. You can try to find the bound on variance of A hat when B is a known parameter and compare with the above bound. We have found a bound when both A and B are unknown, but suppose B is known, then try to find out the bound on the variance of A hat and compare with this bound. Practical importance of CRLV. Cramer lower bound sets a bound on the variance of an unbiased estimator. We cannot have an unbiased estimator with a variance lower than the CRLV. If CRLV is achieved by an unbiased estimator theta hat, then theta hat is the MVUE. So, that is one important aspect, because MVUE will be the CRLV. The CR theorem, Cramer theorem, tells us the exact condition on del L del theta for achieving the CRLV. If this condition is not satisfied, we never achieve it. The CRLV is a benchmark on the performance of an unbiased estimator. While designing an unbiased estimator, we have to ascertain the closeness of its variance to the CRLV. There is a class of estimators that asymptotically achieves the CRLV. Let us summarize the lecture. First, Cramer theorem, variance of theta hat is always greater than equal to 1 by I theta. It gives the lower bound for the variance of an unbiased estimator. Theta hat is an unbiased estimator of theta. The CRLV is reached if and only if del L del theta is equal to I theta into theta hat minus theta. Cramer theorem for the unbiased estimator of a function is given by variance of g hat theta is greater than equal to g dash theta whole square divided by I theta, where g dash theta is the derivative of g theta with respect to theta. This CRLV is achieved if and only if del L del theta is equal to I theta into g hat theta, that estimator minus g theta. This is the condition for achieving the CRLV by g hat theta. CR theorem is extended to an unbiased estimator theta hat of a vector parameter theta, which is given by theta 1, theta 2 up to theta k transpose, and it is given in terms of Fisher information matrix I theta. This is a matrix, it is given by del L del theta, this is a vector into del L del theta transpose. So, this matrix is the Fisher information matrix. Fisher information matrix is also given by this expression I theta matrix is equal to minus expectation of del 2 L del theta 1 square, del 2 L del theta 1 del theta 2, like that, del 2 L del theta 1 del theta k, and going this way last row will be del 2 L del theta k del theta 1 del 2 L del theta k del theta 2, like that, del 2 L del theta k square. Cramer theorem for multiple parameters. The covariance matrix C theta hat of any unbiased estimator theta hat satisfies, this is covariance matrix minus inverse of information matrix will always greater than equal to 0 matrix. This implying that covariance matrix minus inverse of information matrix is a positive semi-definite matrix. And similarly, this CRLB is reached if del L del theta, this is a vector, is equal to I theta matrix into theta hat minus theta vector. If the MVUE reaches the CRLB, it can be obtained through the factorization condition del L del theta is equal to I theta into theta hat minus theta. However, the CRLB may not be achieved by the MVUE. We will discuss another approach to find MVUE in the next lecture. Thank you.